We will now focus on qubit control. We envision that we have a single hole in a germanium quantum dot, and we want to control that hole, the spin state of that hole, to define qubit operations. There are varieties of ways of doing that. Maybe the simplest way would be to make use of a strip line. So imagine either an electron or a hole in a quantum dot, as you see here, and then we have a metallic line through which we drive a current. Now if we apply an AC current, then this current will generate an AC magnetic field, as you see in the image. If this AC magnetic field is orthogonal to the static magnetic field that we generated to create the Zeeman states, then this will result in off-diagonal terms in a 2x2 matrix. If it's on resonance, with the more precession of the qubit, it will induce qubit rotations. And so this is a very elegant way to control qubits. There are also some challenges. For example, there's a large current required to control single qubit. Also, the generated magnetic field is not very local. It will be everywhere where this strip line is. And so if one envision an array of qubits, then it may mean that one is addressing many qubits. Or if there's some way to differentiate between the qubits, for example, each qubit has a different Zeeman energy or so, then maybe a lot of energy is going to be wasted and leading to power dissipation. Finally, this type of control is usually not that fast, and it's on the order of a few hundred kilohertz to a megahertz or so, leading to microsecond timescales for qubit operations. A faster method may be by including a nanomagnet. So instead of generating AC current, there's a nanomagnet with a field gradient. And so if we now displace the electron or the hole in this field gradient, then effectively we're generating an AC magnetic field. And again, if that AC magnetic field is orthogonal to our static field, then in the same way we're driving qubit rotations. Supplying electric fields to a system is more convenient than supplying magnetic signals, and thus faster qubit operations are possible. We see using this method that typically somewhere between 1 and 10 megahertz is a type of speed to drive qubit rotations. However, in this method, it's not clear how one would scale to larger systems, in particular in 2 dimensions. Why? Well, we will need to have a field gradient that allows for qubit rotations, but we don't want to have a field gradient that allows for qubit decoherence. So any field that's on the longitudinal axis of the matrix may lead to decoherence. And so we want to avoid that. And so this combination to have no decoherence, but having a field gradient, as well as giving individual qubit addressability, is at the moment an open challenge. However, we do see that in these small qubit systems, this is a very good approach and very effective. There's a third method, and that's making use of the spin-orbit interactions. And that's actually what we're making use of for holes in germanium. So if we now displace an electron in a quantum dot, then these electric fields also generate an effective AC magnetic field through these spin-orbit interactions. These spin-orbit interactions can be rather significant, stronger than the artificial spin-orbit interactions via nanomagnet, and so qubit rotations here can be rather fast. It's also intrinsic, meaning that if we would have a way of building a 2-dimensional system, one can imagine still to have individual qubit operation. With spin-orbit interaction, it's the question, what will it do with the coherence? Can we have long quantum coherence and still have good addressability and fast operations? And this is still very much a question which is under study. But that we can electrically control whole qubits in germanium using these spin-orbit interactions is clear. For example, here you see Rabi rotations in a 4-qubit system. And from this graph, you see virtually no decay over many qubit rotations in the system, just by applying an electric tone to one of these gates at the Lamarck position of the individual qubits. Now, we're calling a single spin qubit often a loss DiVincenzo qubit. And maybe you have different ways of controlling what we then call loss DiVincenzo qubit. But this is actually not what they had in mind with their initial paper. So already imagine that it's good to study this paper and perhaps to focus on this figure 1 of that paper. And you see here that the spins of these two quantum dots have a slightly different alignment. They have a slightly different spin quantization axis. And that quantization axis can also be used to drive very effective qubit rotations. And so in particular in germanium, where there are strong spin-orbit interactions, the hole is not described by G factor, by G tensor. And it turns out that this G tensor, the difference between different qubits can be significant. I have almost a 50 degrees change in a G tensor from one dot to another dot. This may be unintentional, because maybe the heterostructure is slightly different, strain is slightly different, or maybe the electric fields are slightly different. One can also imagine that one is implementing this in a dedicated way. For example, to have smaller and larger quantum dots, or quantum dots with a certain geometry, or maybe making use of multi-quantum Hall systems. But anyways, if we have a double dot system, and if we displace a hole from one to the other dot, and do this at the right way, we can make very fast and efficient qubit rotations. And so this is something that we're exploring right now. And here you see some first experiments, where you have a double dot system, where we initialize in state spin down, and then we're pulsing a hole from one dot to another empty dot, and doing this very fast, and then rotate back. Now what happens is that this hole in the state spin down, when it's pulsed to the other quantum dot has a different quantization axis. So from the other quantum dot's perspective, it's no longer a basis state, but it's in some kind of superposition state. So if we wait in that quantum dot, the spin is going to rotate, because any superposition in time will lead to a phase evolution. Okay, so we will acquire a phase in the other quantum dot. When we then pulse back to the original dot, we will end up in a different state, because this phase rotation is now going to lead to rotation in the basis of the other dot. Then again, we can wait some time in the other dot before pulsing back. And so by pulsing back and forth, one can very efficiently and fast implement qubit rotations. So instead of using a microwave signal, we just need to apply a few pulses back and forth, where now the qubit operation is no longer of the speed of the AC magnetic field or effective field, but the qubit operation are at the speed of the Lamarck precession. And so one can make very fast and high fidelity operation. And here you see an example where you, for example, apply a generation of pi rotations after each other after carefully optimizing all these timings. Many things are unknown here. This is in one way, a very new way of control. It's also a very old way, in the sense that this was actually the original qubit proposed 25 years back. It may offer very low field operation, because we're now rotating, making qubit operation with a Lamarck precession, which are still significant, even at small fields of, let's say, a few millitesla or so. Coherence typically is much longer as low magnetic fields. Operation can be fast. There's low power dissipation. So we already, before in exploring the different qubit types, so like some qubits, such as the single triplet or the exchange only or the quantum dot hybrid qubits, are advantageous, because these are kind of low power methods implementations as compared to microwave driving. This loss DiVincenzo is also a low power implementation, and perhaps the lowest power implementation. There's also very little crosstalk. In particular, the crosstalk is mainly Z-phase rotations, which may be virtually updated in the reference clock. And no actual qubit rotations are due to crosstalk. And finally, there's true local addressability. We like to think that electrical signals lead to local addressability, but in the end, this localness is still several quantum dots large. By making use of a pulse, it's becoming possible to work in a virtual framework where this local addressability may be true at the single qubit level. At the same time, this field is not well studied, and many challenges may be ahead that we don't know. And so it makes sense to put focus on this qubit type.